All right, so here we are in 12.4 on the normal distribution. So what we're going to learn is we're going to recognize characteristics of normal distributions. We're going to understand the 68, 95, 99.7 rule. We're going to find scores at a specific standard deviation from the mean. We're going to use the 68, 95, 99.7 rule. We're going to convert a data item to a z-score. We're going to understand percentiles and quartiles. We're going to use and interpret margins of error. And finally, we're going to recognize distributions that are not normal. All right, so suppose that a researcher selects a random sample of 100 adult males, measuring their heights, and constructs a histogram for the data. The graph is shown in figure 1214a below. So this is the first top left one here. All right, so that's going to be this one. Now, B and C illustrate what happens as the sample size increases. So now we increase it a little bit more. So we got B and we increase it a little bit more. And then we have C. Well, probably a lot more, but we're increasing it. Now, if you were to unfold the figure C down the middle and look at that, if I can draw a sort of line, if we would fold this over here, it looks like it's pretty much going to be left side fitting the right side. And as we move out from the middle, the heights of the bars are the same to the left and to the right. Now, this means that this is kind of symmetric about this middle part, which is called the mean. Okay. Now, these histograms then therefore are called symmetric, and as the sample size increases, so does the graph symmetry. And if it were possible to measure the heights of all adult males, the entire population, the histogram would approach what we call the normal distribution, which is what we see here. This would be the normal distribution. And this distribution is sometimes called the bell curve or the Gaussian distribution because it's named after the German mathematician Carl Friedrich Gauss, and that was when they were around. So, small amounts of data, we have something that's kind of, yeah, it's not super symmetric. The more we add, it's getting a little bit more, and the more we add, we get more. And this would be, the whole population. It would be this bell curve here. Now, this is what, grades are based on. This would be the C, and, the A's would be over here, and your F's would be over here. But, because we only have so many people in the class, we never get anything that really resembles a bell curve. It might look more like this, where it's more skewed to the F's and then the A's are over here, or maybe it could get a little bit higher. But, this is why things look and don't look like they do, because they have too few of sample, or if they have the whole population, we get something nice like the normal distribution. Now, figure 12D, this normal distribution is bell-shaped and it's symmetric about a vertical line through the center. Now, furthermore, in this case, the mean, the median, and the mode of a normal distribution are all equal, and they're located right here at this center. So we have, X bar, the median, and the mode are all at that point there. So that's kind of a nice thing about a normal distribution. Now, the shape of the normal distribution depends on the mean and the standard deviation. So figure 1215 down here illustrates that. Kind of a small picture, but that's the way it is. It has three normal distributions with the same mean. So if you notice, they all line up right here at this mean part. But because they have different standard deviations, they have different shapes. So as the standard deviation increases, the distribution becomes more dispersed or spread out, but it still remains a symmetric bell shape. So here we have a very small standard deviation. Here the standard deviation is getting bigger, and here our standard deviation is even larger. Now, the normal distribution provides a wonderful model for all kinds of phenomena because many sets of data items closely resemble this population distribution. For example, heights and weights of adult males, intelligent quotients, the IQ values, their SAT scores, prices paid for a new car model, lifespans of light bulbs, all these tend to cluster around a mean, and then they have some kind of standard deviation, which either makes them, have a big peak here, or they kind of flatten out and have a more flat kind of shape of a curve. All right, so the more an item differs from the means, it's actually less likely to occur. So further away from that mean, it's less likely to occur. So, that's kind of a standard deviation, has a lot of standard deviations, and so it's going to be less likely to occur way out here. Now, the normal distribution is used to make predictions about an entire population using data from just a sample. Now, this section we focus on the characteristics and applications of the normal distribution. And here we're going to look at the standard deviation and z-scores in a normal distribution. So the standard deviation plays a crucial role in the normal distribution and is summarized as the 68, 95, 97.7, 99.7 rule. Now, this is what it looks like in a picture model. So we still have our normal distribution. We have our mean right down the center here. And then what we're saying is we have this rule called the 68. Well, that means 60%, 8% of the data fall within one standard deviation of the mean in both directions, so half and half. 95% of the data items follow within two standard deviations of the mean, so two this way, two this way. And 99.7% of the data fall within three standard deviations of the mean to the left and to the right. So that's how we're getting that. So 99% of all the data is going to follow within three standard deviations, whereas 95% within two and 68% within one. Now, if we only are saying, okay, well, what if we want only this piece here? How much is going to be within that standard, within that piece here? Well, we know the whole thing is 68 from all the pink. So if we do half of it, just to one side, that means 34% is going to be to the right, and same thing, 34% will be to the left. And then we can do similarly for 95%. 95%, half of that will be on this right side, or half of it will be on the left side. So that's kind of how we can use our 68, 95, 99.7 rule and the normal distribution to kind of figure out how much area is there under that curve. All right. So going back to this illustration without markings on it, it's shown that a very small percentage of the data in a normal distribution lies more than three standard deviations. So again, 99.7 is within three, and so we just have that little bit going this way, and we have that little bit going that way, which is basically, the 0.3%, 1.5% each direction going here, and 1.5% going this direction. And so as we move from the mean, the curve falls rapidly, as we can see here. So we have our mean, it falls rapidly here, and it approaches, but it never touches this horizontal axis. So that means the further and further we get out, no matter how far out we go, it's not actually touching that x-axis. It just gets really close. And so we're really worried mostly about just this individual part here from the 99.7. So the range of the normal distribution is infinite. It keeps going on forever. So no matter how far we go, it's never down to the thing. We could go out, 50 standard deviations, and you're still going to have an infinitesimally small amount that's still out there that is showing under the curve. So, you might get out to, you know, 50 standard deviations. And if you could look at a really, really small scale, it's still going to have something under that curve out at that long distance. All right, so let's use our knowledge of that and look at this one. It says female adult heights in North America are approximately normally distributed. So that means we have, that normal bell curve, okay? And it has a mean, well, so that means this is going to be 65 inches and a standard deviation. So S is going to be equal to 3.5 inches. So what it wants to do is find the height that's three standard deviations above the mean. So we want to be above three standard deviations. So for A, what we're going to do is we're going to take our mean, 65, plus 3 times the standard deviation, which is 3.5, and figure out what that is. So if we do that, that's going to be, we go to our calculator, 65 plus 3.5 times 3, and we get 75.5 is where we're going to be at for that. 75.5 inches is 3 standard deviations above the mean. Now, what about 2 standard deviations below the mean? Well, that's going to be 65. Now we're going 2 below, so we're only going 2 down. So we're going to take 65 minus 2 times 3.5. Well, that's 7, so we subtract that. That's going to be, 58 inches. Okay, and so that will be where we're at, 2 standard deviations below. So this is 58. This over here is going to be the 75.5. And so that's how we can use our standard deviations and our means to figure out where we are on the chart as far as either 3 above or 2 below. All right, so let's stop there and we'll come back for some more.